So after the typical unnecessary animation, we have kind of a fun problem here. One that I believe I saw as a problem of the day in the Ole Miss math contest at some point. I like this question because there's not really any explanation necessary. The picture kind of tells you everything you need to know. We just need to figure out the length of the red line segment that's defined by the green chord of length 32 and one of the white diameters of length 40. One thing I don't like about this problem is it's a little hard to get started, but once you get started, it's kind of fun. So maybe right off the bat, it's a good time to use a hint.
Apply the right angle corollary to the inscribed angle theorem.
That sounds a lot worse than it is. The inscribed angle theorem just says that in a circle with center C, the angle pictured in blue is twice as big as the angle pictured in orange. And that's true no matter where you put A, B, and D. And that's a really famous theorem. It dates at least all the way back to 300 BC, where it showed up in Euclid's Elements, a series of books considered by some the greatest publication of all time. Anyways, to see if this is true, we'll start with kind of a special case of our picture. One where AB is a diameter of the circle, and D is halfway in between A and B. My first claim is that the angle pictured in orange is 90 degrees. To show why this is true, all we need to do is add the segment connecting C and D, and recognize that that creates two right isosceles triangles. They're right triangles because D is halfway between A and B, and they're isosceles because two of the legs in each triangle are radii of the circle. So because the sum of the interior angles in any triangle is 180 degrees, and our right angle uses up 90 of those, we only have 90 left for the two congruent angles. So in triangle BCD, the angles at vertices B and D must both measure 45 degrees. And the same logic holds in triangle ACD. The two 45-degree angles at vertex D sum to 90 degrees, which was the claim that I was trying to prove. And you're like, right, but that's not the inscribed angle theorem. And that's true, but note that since AB is a diameter, it's a straight line, so angle ACB would measure 180 degrees. And 90 degrees is half of 180 degrees. So in this special case, the inscribed angle theorem holds. Now look at triangle BCD. Watch what happens when I move vertex B to change angle C. Maybe I'll make it, 20 degrees bigger. I still only have 180 degrees to play with in triangle BCD, so I have 20 degrees less to split between the angles at vertex B and vertex D. So each vertex individually is going to be 10 less. By adding 20 degrees to the angle at vertex C, which, by the way, took away 20 degrees from the angle pictured in blue, I've taken away 10 degrees from the angle pictured in orange. The change in the orange angle was felt half as much as the change in the blue angle. And the same thing happens if I move vertex A to change the angle at vertex C. If I make the angle at C smaller by 40 degrees, then the blue angle increases by 40 degrees. And because I've decreased the angle at C by 40 degrees, I have 40 degrees more to play with in the angles at vertex A and D. So 20 more each. Net effect is we increased blue by 40 and increased orange by 20. So we started out with a blue angle twice as big as the orange angle, and any change affects the blue angle twice as much as the orange angle. So the blue angle will always be twice as big as the orange angle, which is exactly the inscribed angle theorem. Oh, cool, but didn't Hector say something about the right angle corollary to the inscribed angle theorem? Yeah, but that's even easier. All that's saying is if you're lucky enough to have an angle in blue of exactly 180 degrees, in other words, a straight line through the center, in other words, a diameter, then the angle in orange has to be 90 degrees. Put differently, an angle inscribed in a semicircle will always be a right angle. Okay, but how's that relevant in this problem? We aren't given any angles inscribed in a semicircle. That's true, but look, the side length we're trying to find is one of the legs of a right triangle. Can you create another right triangle that would be similar to this right triangle? Look at this one. Both the triangle in green and the triangle in red share an angle, so that's one pair of congruent angles. And because the triangle in green contains an angle inscribed in a semicircle, that angle is a right angle, giving us a second pair of congruent angles. Using the fact that the sum of the interior angles in any triangle is 180 degrees, if we have two pair of congruent angles, we must have three pair of congruent angles. So the triangle in green and the triangle in red are similar. The hypotenuse of the green triangle is just the diameter of the circle, so it has length 40. And the longer of the two legs in the green triangle is the chord whose length was given to us to be 32. In the red triangle, the longer of the two legs is the radius of the circle, so it has length 20. And the shorter of the two legs is the length we're trying to figure out. Maybe it's easier to see if we separate the two triangles and reflect the one in red to emphasize the similarity. To figure out the missing length in the green triangle, we can either just apply Pythagorean theorem or recognize that 32 and 40 are 8 times 4 and 5 respectively. And since a 3, 4, 5 right triangle is a thing, the missing leg must be 8 times 3 or 24. Comparing the longer legs in the two triangles, we see that the lengths of the sides in the red triangle are 5/8 the lengths of the corresponding sides in the green triangle. So x is 5/8 of 24, or 15. That was quick. How about a challenge question before I go? I'm going to need a circle. Ooh, that's a nice one. And now I need a 9-pointed star with the points equally spread out around this circle. The question is just to determine the measure of this angle. Grace me with your thoughts, questions, and solutions in the comments if you feel like it.